Marimar is made easy, no more fear. Target online class, we got you. Wherever you want it from, we got what you need. Target online class, we got you.
Good day, everyone. Once again, you are welcome to Target online class. Just as I've introduced the set of numbers. So the first set of numbers. The first set of numbers are called the natural numbers. The natural numbers. So denoted, this one is denoted as n, as we have it on the bottom. Good day, viewers all over the world. You are welcome to Toydale online class. So today we want to look at examples on semigroups, monoids, groups, and abelian groups. When I introduced a group theory, we talked about 5 different concepts. The first one is groupoid. We talked about semigroups. We talked about monoid. So we talked about groups. Then finally we talked about abelian groups. So I have a video on this concept. Groupoid will satisfy the closure property. Semigroup will satisfy the closure and associative property. Monoids will satisfy closure, associative property, and existence of identity elements. While group will satisfy 4 properties: closure, associativity, existence of identity element, and existence of inverse elements. Then abelian group, there is a group that is commutative. So we just add commutative property to groups to get an abelian group. So today we want to look at the examples on each of the following. So we take the first example. The first example says that a binary operation, I start to abbreviate binary operation as BO, asterisk, is divine on set S. S is defined as A, B, C, D, E. That is set X by the entries in the table below. So this is the table. We have asterisk here. We have A, B, C, D, E. This is the table. We also have A, B, C, D, E. So here we have E, C, A, B, D. Then the second one we have D, E, B, A, C. Then we have A, B, C, D, E. Then we have C, A, D, E, B. Then lastly we have B, D, E, C, A. So this is the table. So the first question, A, is that is X under asterisk a semigroup? Is it a semigroup? Question mark. Then B, now say justify your claim. The claim in A. Justify the claim in A. So if it's a semigroup, you justify. If it's not a semigroup, you justify. Then the third one, the question now says, what is the identity? What is the identity element? What is the identity element of S under the binary operation asterisk? So these are the 3 questions that we want to answer. So these are the 3 questions that we want to answer. So now let's look at the question critically. What are we given and what are we required to find? This is the binary operation. It's defined on the set. There are 5 elements in this set: A, B, C, D. By this entry, the set is defined as this. The question now asks that is S, asterisk a semigroup? What will make this a semigroup? S, asterisk will be a semigroup. One, if it is closed. Well, two, and if we are able to verify associative property. So those are the 2 things that we are going to look at. So is this a semigroup? Is either you say yes or no. But we are going to check for, of course, it is closed. It is closed because the solution. No, since we know we know the question now, so I can rub it off. So let me just do the solution here. Solution. Solution. The first question, is it a semigroup? Of course, this is closed. It is closed because there are 5 elements in that set: A, B, C, D, and each lines, each row and column consists of the 5 elements. So A, the first one is that it is closed. That is, we say X asterisk is closed. Is closed. Or I can say S is closed. S is closed under the binary operation asterisk. It is closed. Why is it closed? If you check all the vertical and horizontal entries here, they all consist of the 5 elements that we have in X. So it is closed. That's the first property. Then the second property, we want to test for associative property. So once we are able to test for associative property, the closure property is closed. Under associative property, let's check. So if we pick A asterisk B asterisk C, are we going to get the same thing as say A asterisk then B asterisk C? Let's look at A asterisk B is C. That is C. Then we now have C asterisk C. C asterisk C is C. Then let's go to this side. We have A asterisk. What is B asterisk C? B asterisk C is B. Then what is A? A asterisk B is C. It's equal to C. In that case, it must be this associative property must hold for all. So now let's look at B. Let's take another example. B asterisk D asterisk E. Will it be the same thing as B asterisk into bracket D asterisk E? Let's check. What is B asterisk D? B asterisk D is A. So we have A asterisk E. What is A asterisk E? That is D. Are we going to get the same thing as B asterisk? What is D asterisk E? D asterisk E is B. So what is B asterisk B? That is E. In this case now, we are unable to get the same value. It shows that the associative property does not hold for all elements A, B, C that belongs to X. So in this case now, since we are unable to show that the associative property is closed for all, then we say that in this case now, the first question is S. We now say that S asterisk is only a groupoid. Is only a groupoid. Is only a groupoid and not a semigroup. It is not a semigroup because all the elements, 3 elements in under the set S does not hold for all. So it's not a groupoid. So that simply means that A part of the question is that no. Is this a semigroup? No. We have been able to justify. Then the third one is talking about the identity element. So what will be the identity element? The C part of the question. Now, what will be the identity element? Identity element is the neutral element. That is when you say A asterisk E must give us A. That is, this E identity element is a neutral element. That is, when we have A here, operate it with another element under this binary operation, we must get A. So now let's check the table. Where do we get that? A, this is E. But in this case now, we have A asterisk, whatever we have here is A. Look at B asterisk, whatever we have here is B. C asterisk, whatever we have here is C. You realize that all the elements here is the same as what we have here. So we now say that the identity element So the question says, what is the identity element? We now say that the identity element, C, the identity element is C. Why is it C? You realize that A asterisk C gives us A. Look at it. If you look at B also, B asterisk C is also equal to B. C asterisk C is also equal to C. D asterisk C is equal to D. Then E asterisk E, that C is equal to E. So it simply means that C is the identity element under this question. So we have been able to answer the three questions. In this case now, we have been able to answer the three questions. So we go to another question. Let's go to another question, question 2. Let's go to another question, question 2. The question says that on Z, that is on the set of integers, define on Z, defined a binary operation asterisk by A asterisk B equal to A plus B minus 1 for all A, B belongs to integers. The first question now says that we should show that Z, that is integers, under binary operation is a monoid. Of course, for this to be a monoid, the three properties must be satisfied. The three properties must be satisfied. Then B, we also to check whether let's check whether or not integer under binary operation is a group. So solution, we know the first thing to do. For us to show that integer under binary operation is, for us to show that is a monoid, we test for closure property, associative property, and existence of identity element. So that's what we are going to test for. So let's check. Let's check. With that old, yes, we have to check it. The first one is that we test for closure property. That is, for all elements A, B that belongs to this integer. So is it possible to get A asterisk B that will be equal to A minus plus B minus 1 that also belongs to integer? Yes. Irrespective of what this A and B represents. If we add A plus B, it will still belong to Z. Let's say A is equal to 2. And let's say A is equal to minus 5 and B is equal to 2 minus 1. You know, we have minus 1 minus 5 minus 1, that's minus 6 plus 2. That's equal to minus 4. Minus 4 is still part of this set of integers because integers consist of negative, positive, whole numbers, and 0. So irrespective of the value of A and B, which is an integer, if we operate it on this value, we are still going to get it in Z. So closure property is satisfied. Then Roman figure 2, we test for associativity, that is associative property. Associativity, that is for all A, B, C that belongs to Z, we want to show that A asterisk B asterisk C, we want to show that A asterisk B asterisk B, that is, we want to show that A asterisk B asterisk C must be equal to, when I write this, that is, what is A asterisk B is defined as what? A plus B minus 1, then asterisk C. So the next thing is that we are going to view everything that we have here as A. So in this case now, I'm going to have A plus B minus 1, then plus C minus 1. So can I rewrite this? Can I rewrite this to get what we are looking for? That is, in this case now, I'm going to have A plus, let me now rewrite this, B plus C minus 1, then minus 1. So let me rewrite this in this form. Then if I do that, this will be A. Then this will be A plus B plus C minus 1. B plus C minus 1 will be B asterisk C minus 1. That's what we are going to have. Then at the end of the day, when we have A asterisk B, it's not the same thing as A plus B minus 1. So in this case now, this simply means that I'm going to have, instead of this B now, you know, when I have B here, this is ordinary B. A is here, minus 1 is here. So this is A, this is minus 1. Then everything that I have here now, I'll view it as 1. So at the end of the day, I'm going to have A asterisk into bracket B asterisk C. Since I've been able to show, the closure property as we have it on the associative property as I have it on the board, so that condition is also satisfied. Then we go ahead and test for the third one, which is the existence of identity element. Roman figure 3, existence of identity element. Existence. Let's test for the existence of identity element. That is the third property. Once we are able to show this, it shows that Z under asterisk is a monoid. So under this, we say for all A that belongs to Z, that integer, there exists E that belongs to Z, such that A asterisk E, which is same thing as E asterisk A, must be equal to A. That is, in this case now, A asterisk B is given as this. So A asterisk E will give us A plus E minus 1 will be equal to A. A plus E minus 1 is equal to A. Then in this case now, we have E minus 1 to be equal to A minus A. Or I can say E is equal to A minus A plus 1. This will take care of this. E is equal to 1. So the identity element is 1. The identity element is 1. So therefore, Z integers under this is a monoid. It's a monoid because we have been able to test for the three properties. Then the second one is now has that, is this a group? For this to be a group now, the second part of the question, we have tested for the three properties out of the 4 that makes a non-empty set a group under a binary operation. So we only test for existence of identity element. We now say for all A that belongs to integer, there is this A inverse that belongs to integer, such that A asterisk A integer, A inverse must, or A inverse asterisk A must give us the identity element. That is, we want to show for existence of inverse element. So in this case now, A asterisk is defined as this. So this will be defined as A plus A inverse minus 1 will be equal to E. Then what is E? E is defined as 1. So we now have A plus A inverse minus 1 equal to 1. A inverse will now be equal to minus, by the time minus, we have 1 minus 1 plus 1 minus A. So A inverse is equal to 2 minus A. A inverse is equal to 2 minus A. So 2 minus A is actually the inverse element. So 2 minus A is the inverse, of A. So irrespective of what A is, since we have been able to show that this, it has an inverse element, then we now say Z integers under asterisk is a group. So that is what we are asked to do. So we have been able to show that integer under asterisk is a group. So we take one more example. Let's take another example. Okay, let's take another example. Example 3. Let's take another example. And since this is a group, we can also check. We can also say that we can also check for if this group is an abelian group. So if you want to check for abelian, we just test for commutative property, that is A asterisk B. Just show it to be B asterisk A. So if you are able to show that, it shows that that group is also an abelian group, and that is what is expected. If you have to check that is an abelian group, then Roman third question. Let's take another question. In this case now, we have, okay. In this case now, the question says on R, on the set of real numbers, the sets on the set of real number on R, which is set of real number, we define a binary operation. We define a binary operation asterisk by A asterisk B to be equal to A plus B plus 3. That's what we have. The question now says that we should show that the set of real numbers under asterisk is an abelian, group. Okay. So for abelian group, it's the same as commutative group. So for us to be able to show that real number under binary operation is an abelian group, we test for 5 properties. We test for closure, associativity, existence of identity element, existence of inverse element, and commutativity. So those are the 5 properties that we're going to test for. So if you're able to show the five properties, it shows that R set of real numbers under this binary operation is an abelian group. So we start from the first one. So let's start with the closure property. Closure. Let's start with the closure property, the first property. So that one you just say for all A, B that belongs to R, A asterisk B also belongs to R. And of course, what is A asterisk B? A plus B plus 3 will also belongs to R. So set of real number is the largest set under consideration. So any number you think of, either fractional, if the number is fractional, if it is negative or what have you, everything will still be in the set of real number. So it shows that this one is closed. Closure property is satisfied. We go to the second one, which is associative property. Associativity. Under this associativity now, we now say that for all A, B, C that belongs to R, we want to show, if we're able to show that A asterisk B asterisk C is equal to A asterisk B then asterisk C. This is what we want to show, or vice versa. Or we can say A asterisk B then before C to be equal to A asterisk then this will be B asterisk C. So if I'm able to show that this is equal to this, then we are on the safer side. Now let's start. A asterisk B asterisk C will be equal to, what is A asterisk B? That is, we have A plus B plus 3, then asterisk C. So we are going to view everything now, everything that we have here as A here. So in this case, I'm going to have A plus B plus 3, then this is plus C will now be equal to plus 3. This is what we are going to get. So can I rewrite this? Of course, yes. That will be A plus, I will now combine B plus C plus 3, then plus 3. So what would that give us? I'm going to continue from there. So from there, now from here now, I'm going to have this will be equal to A. It will be equal to A plus, then here I have B asterisk C plus 3. Then finally, I will view everything here. I'll view it as 1. This will now be A asterisk into bracket B asterisk C. So since we have been able to show that A asterisk B all into brackets asterisk C is equal to this, then it shows that the second property is satisfied. We go to the third one, which is the existence of identity elements. So this is the third property. So how do we show that? How do we show the third property? So this is what we do. We just say for all A that belongs to R, set of real number, there exists identity element that belongs to R such that A asterisk E is equal to E asterisk A and is equal to A. So A asterisk B is A asterisk E will now be, this will now be A plus E plus 3 to be equal to A. Let's make E substitute formula. E will now be equal to A minus 3. Then this will take care of this. So E is equal to minus 3. So the here now the identity element is 3. So we go to the fourth property, which is existence of inverse elements. Then under inverse element, we say for all A that belongs to set of real numbers, there exists A inverse that belongs to R such that A asterisk A inverse, which is same thing as A inverse asterisk A, must give us identity element, because we use the inverse element to get the identity element. So in this case now, we now say A asterisk A inverse is equal to identity element. What is A asterisk A inverse? A asterisk A inverse will be A plus A inverse, then minus 3 will be equal to minus 3. We have gotten the value of this to minus 3. So let's make A inverse substitute formula. This will be equal to minus 3 minus A. And that's what we are going to get. At the end of the day, we are going to have minus 6 minus A. Then here, I'm going to have minus into bracket 6 plus A. So this is the inverse elements under the set of real numbers. So the last thing that will make that set abelian is commutative property, commutativity. That is, in this case, now that commutativity, we just say for all A, B that belongs to R, A asterisk B must be equal to B asterisk A. So what is A asterisk B? Is defined as A plus B minus 3, right? That's what we have. No, it's plus 3. This is defined as is plus 3. So here is plus 3. So we have to use plus 3 to get an Abelian group. So we have properties that is required to get an Abelian group. So we have been able to show the 5 properties. So that is that about the Abelian group. So I want us to just go through standard textbooks to check for further examples that we can actually have under group and semi-group. And if you have any issue, if you have any problem under example on group theory, you can just type it in the comment section. I promise to go over this comment section and provide solution to any question that you are unable to solve. So I'd love to stop here because of our time. We are going to continue from there by the grace of God some other time. Thank you and God bless you all.